A could either take 1 or 0, you see. So you realize that it either takes 0 or 1 at any given time. It can never be both. So you see that is it. So you can see that we are connecting. You see if it is 0, then that is a false statement. If it is 1, you see that is it. It is a true statement. And you're told that also another difference is that while conjunction, disjunction and negation, of course, represented by these terms commonly used in propositional logic. The binary operations plus, and you can see that we have this and, of course, represented, we may as well call it multiplication in that case, and complement, which is bar, are used in Boolean algebra. Both logical connectives and Boolean operations perform similar tasks in combining or manipulating truth values. And although they are defined slightly different, in that is it, and you can see, I've given you some tabular presentation of the differences. Why are guys raising their hands again? Maybe there could be an issue. Let me see. Okay. Oh, there are fellows who are getting in, maybe. Okay, maybe. Oh, yes, I can see. Let me admit this guy. And please kindly mute or catch now that you are in, kindly, or catch for the cup. Okay, that is it. So you can see this. This is in propositional logic. You can see this one is conjunction, what we've done before. But when you talk about Boolean algebra, you can see that. You can see 1 by 1. You see that is 1, 1 by 0, 0. You see that is it. So you can see false is represented by 0, 0, 0. You can see in that case. And when you talk about the disjunction, you can see that that is in propositional logic. Of course, that is disjunction. In Boolean algebra, in that case, that is plus, and you can see 1 plus 1 in that case. To be very careful not to say that that is 2. That is 1. Of course, there is when both are true. You see that is the case. This one is 1. That is 1, and of course, it can only be false for the case where it takes up the value 0. For the case where both are take the value 0. Yeah, when we talk about this one is a negation. And of course, when you're talking about Boolean algebra, we're talking about complement. And of course, here, when we combine, there is a conjunction of that is A and its negation. Of course, that is false. Also, that is the A and its negation. In this case, when A is false, of course, that is false. And for the case where we have a disjunction, you can see, I think this is something that we mentioned last time. Of course, in both cases, you find that those ones are true. But when we cross over to Boolean algebra, you see that for true, we have 1. For false, we have 0. For false, we have 0. That is it. And you see this one is 0, 0. So you can see that there is a similarity between that is and of course, a conjunction. And or any disjunction. You can see that, yes. And again, because of that, you notice that even the properties of Boolean algebra is similar to the properties of propositional logic. And there are quite a number of properties of propositional logic. One of them is A disjunction B is no different from B disjunction A. It doesn't matter the order in which we present the propositions. You notice that it's still one and the same thing. These are what we call commutative laws. In associative laws, we see that we have 3 here. And in having these 3 propositions, we see that, yes, it doesn't matter which ones start. Even if we start with the first 2, it's no different from starting, you see, with the last 2 and then followed by the first one. That is exactly what we have. And it applies in both and in both or and. You can see in this case, yes, you see again, there is no difference. In that case, that is what we call associativity laws. And the distributive laws, we see that we have, that is, and here is distributive over or. That is distributivity. And again, we see that here we are talking about that is or is distributive over and. And as you can see in this case, you see that is the same as A and B. And A or B, and then and. Of course, we have the brackets here. We see that in that case, or is distributive over and. Under identity laws, we're saying that, of course, we see that A or that is false is this one will be A and true in this case, and the variable 1 is A. Of course, here under complement laws, we're having that is A or its complement in this case will give us 1. Of course, that is it will give us the variable 1. And in this case here, when we're talking about, let me hope that you can see this and you can have an idea. You see, if suppose, this is what we're saying here, suppose A is takes the value 0, of course, the complement of A will take the value 1. So 0 or 1 is 1. And if, of course, if this is 0, and then this one is, of course, this one will be 1, the complement of that. So you notice that 0 and 1 will be 0. Yeah, that is it. So that is, we will have to be very careful there. What we call idempotent laws relate to, that is the same proposition and itself. And we can see in this case, we're talking about A or A is A and A is A. Absorption laws, we see that we notice that here the AB is absorbed by A to get A. And the same case applies here. A is absorbed by, that is A or B when we have A and. Okay, kindly please allow me to admit someone. I think somebody wants to be admitted. Or Tagwi Kamau, maybe he has something. I think you've raised your hand. And after all, you just felt like raising your hand, maybe. It's okay. It's no worry. Maybe let me see whether I think that I'm not seeing anyone who wants to get in. So we see that now we have domination laws. We see in this case, we have A, of course, or 1. And in this case, this one gives takes up the value 1. A and that is the value 0 is that is 0. And now we go to what we call the axiomatic definition of Boolean algebra. And here, this is when we define a Boolean algebra with respect to a set of axioms or a set of rules. And these rules relate to the elements and operations that it must satisfy. And we have 4 axioms in this case. One of them is what we call closure. And I think we've talked about closure property a number of times, and especially even when we're dealing with groups and their rules. When we talk about closure, then you see we're talking of something that relates to, you see, whenever you engage a certain operation, you still get an element that belongs to, let's say if we're talking about a set, that is the case. If we're talking about now, in this case, we're talking about maybe propositions, then we see that, yes, they belong there. And you can see here, you're told that for any elements A and B, the results of A and B, and no, this is not A and this is A or B, and A and B are also in the set of Boolean values. You see, what we're being told in this case is that A or B here gives us either 0 or 1, depending on the values that A and B take. The same case applies here. A and B is either 0 or 1, depending on what A and B are. That is it. And you see in that case, you'll find that in as far as Boolean algebra is, our set of reference will always be 0, 1. That is, it will be a set where they're consisting of the values 0 and 1. And those are the ones that the Boolean variables can take. You see, that is it. So here, when we talk about identity, we say that we have identity elements. When it comes to OR, we have the identity to be 0. And the identity for 1 for multiplication, you can see this, where we call this AND. We silently, many times, we don't refer to it as such a multiplication. So we have that is 0 and 1. And here, and I think you can see this, when we're talking about OR, is literally there is an identity. Look at what is happening here. We have what we call identity laws. You can see, you realize that this one doesn't change A. And again, the identity in as far as A is concerned here with respect to AND is 1. And that is exactly what is being mentioned here. And also here now the third property or the third rule is what we call complement. And every A has a complement, of course, that is A complement denoted by that. And you realize these ones satisfy, I think there are some laws that we've talked about here. We have what we call complement laws. That is where we derive the term complement laws. So you realize that here we have the case of identity law satisfied in as far as the axiomatic definition of Boolean algebra is concerned. And again, we find that the complement laws also are satisfied. And I think we talked about that. You can see exactly what we have here. And another property that is satisfied is what we call distributivity. And that is exactly what we talked about in as far as the properties of Boolean algebra in 3. And that is exactly what we're seeing here, where we have here and distributive over or. Here is or distributive over and. That is it. And for us to have a better understanding of this, maybe what we do in this case is to see how we use these laws to simplify some, you see, some expressions. And look at this, you are asked to use a specific example of values of A, B, and C to verify the distributive law in Boolean algebra. And in this case, you see we've picked A to be equal to 1. And as I said very well, you notice that A, B, C take either 0, 1, nothing else. We confine ourselves within that. A is either true or false, B is either true or false, C is either true or false, and that is it. And we've picked a specific case. It is not to say that we confine ourselves within this, no. We could even go, some fellow could take A to be 0, B to be equal to 1, C to be equal to 0, and so on. Any could do. So that should not be considered to be just cast on stone. No, that is not the case. So if having taken this 1, 0, 1, we look at the left-hand side, of course, that is 1, of course, and we have now in brackets that is B or C. There is need for an equal sign here. Apparently, we don't have an equal sign here. There should have been an equal sign here. We see this is 1, and then this one is 0, that one is 1. Okay, that is how we have this. And we see that 0 or 1 is 1, and I think that is something that you know. But now, before you do that, instead you see, because we're using distributivity property, then what we see in this case is that this one is the same as 1 and 0 plus 1 and 1. You can see that is exactly what we have here. And 1 and 0 is 0, and 1 and 1 is 1. And that is why we have this one to be 0, of course, or 1. And what we shall have in as far as 0 or 1 is 1. I would want to see now, look at the right-hand side to see whether it is equal to the left-hand side. And on the right-hand side, we see that, yes, the right-hand side, of course, the distributive law. You see, this is it. Yes, so let's see what happens in this, and as far as the right-hand side is concerned. The right-hand side in this case is exactly what we have here. So we see that that is exactly what brings us to this. However, I would wish to mention this. The alternative to this is not exactly what we've done here. I would wish to mention something. Let me correct something here, and please correct from your end. You see, because we are relating the right-hand side and the left-hand side, then don't use distributive laws in as far as the left-hand side is concerned. So I would suggest that you do away with this. This one, look at this. So please, this one should be this. Let me have that. That is A and, sorry. A and you see, this one is the left-hand side. That is exactly what we have here. So this one actually comes out to exactly what I had mentioned earlier. You see that is 1 and then we have a 0 or 1. 0 or 1, you see, look at that carefully. 0 or 1 in this case is 1. So we shall have 1 and 1. And 1 and 1 is equal to 1. And that is the left-hand side. Kindly please correct that. This one should not be this way. And we are not applying the right-hand side. Rather, what we're doing is to analyze the left-hand side as it is. right hand side, so that when we compare the two, we see if they are equal, well and good. We say then that it leaves the distributive law verified. Okay. I thought there is someone who wants to join. I can see there is none. Okay. So duality, there is something called duality in Boolean algebra. And this also applies to not only duality, it is also in propositional logic. And not only that, it also applies to set theory. If you still remember the laws of the algebra of sets, where we have union and intersection, you notice that the duality of a certain expression, let's say in the form of a Boolean expression, is obtained simply by interchanging. Like in this case, you can see that if we have that is or, we replace it with and. If we have and, you replace it with or. If we have one, you replace it with zero. If you have zero, you replace it with one, and that will give you the dual. And you can see here I've noted in propositional logic, for example, the dual of this, you simply replace that with you see this one is a disjunction, you replace it with a conjunction. And therefore, in that spirit, then, based on exactly what has been mentioned here, the duality of this is simply A and B or C. That is it. You can see that. We've replaced this plus with that, this one by that. And the same case here, you've replaced this and by or, you've replaced or by and that is it. That gives you the duality. Purely that. By any chance you come across that, those are the kind of areas that I consider many times to be areas that are purely to award you free marks. Because you don't struggle in that case. When you're talking about duality, you simply interchange those variables. Or you see, if we're talking about operators, in that case, then you're talking about or and that is it. Now, in again, Boolean algebra, we have what we call a tautology and a contradiction, just in the same way we talked about propositional logic. And of course, you see, you're told that it's a Boolean expression that has one always. You see, it's always true. That is, regardless of the values of the individual variables. A contradiction in Boolean algebra is an expression that results in zero for all combinations of variables. It essentially represents a logically impossible situation, where no matter what values the variables take, the result is always zero. That is it. You can see this. You're asked to determine whether each of the following is a tautology, a fallacy, or neither tautology or a fallacy. And in this case, we have the first expression to be that, the second one is that, and the third one is that. And what do we do in this case? Simple. We have, of course, how many variables do we have here? We have A and B. So in that case, we have A, B. And of course, A either takes 1, 1. You see, we have the combinations of all these, that is of these the values, 1, 1. If you were to go to propositional logic, that is true, true. This one is true. This one is false, true, and that one is false, false. You know. So I think that is something that you can see. Okay, Braden Mwangi there. You are admitted. Okay. So we have the complement of this, of course. If this one is 1, then the complement that is 0. This one takes up 0. The complement of 0 is 1. That one is 1. And then we see in this case, we have now that is A, the complement of A, and B. A and B, you can see that is 0. This one is 0. This one is 1. This one is 0. And that is why we have that. And now we have A or this one. A or that one is 1. You see 1 or 0 is 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. And therefore, it's neither a tautology nor a fallacy. So you can see that. So here we see in this second case here, this one gives us a contradiction. And you can see again, we have the same combinations because how many are they? These ones are A and B. And so that being the case, then we shall have 1, 1, 1, 0, 0, 1, 0, 0. But then, of course, the complement of that gives us that is, of course, that is 0, 0. And see that 0. This one is 1. That one is 1. And then, of course, this one is A or A complement. You see, this one is giving us 1, 1, 1, 1. You can see that. That is how we are having that. And once we have this, what else do we need? We need B complement so that we can have B and B complement. So we have B complement. We have the, you see that one when it is 0, here the complement is 1. That one is 0. This one is 1. And then, of course, you see this one 1 and 0. 0 and 1 is 0. 1 and 0 is 0. 0 and that, and 0 is that. All these are zeros. And therefore, we say now this one and this one. We have 1 and 0, that is 0, 1 and 0 is 0, 1 and 0 is 0, 1 and 0 is 0. That is where we have all this, and therefore this one is a fallacy or a contradiction. McDonald. Okay. So now, let's look at 2. 2 is a bit tricky. It engages us through the laws of Boolean algebra, or properties of Boolean algebra. You see, you're asked to prove the following Boolean equations using properties of Boolean algebra. And here, oh, maybe I should have mentioned something. In this, you see, we have 3 of them, A, B, C. So what we do in that case, maybe just to give you some hint, we shall have A, B, C. And of course, the first one is 1, 1, 1. The next one is when one of them takes up 0. So in that case, we shall have, you still remember the case of pushing a diagonal. So we shall have 0, 0. So we shall have 1, 1, and then 1, 1 there. And then now we have the other case where we have 2 taking up value 0. And then now we take it as if we are pushing a diagonal that way. So we shall have 1, 1, and then we shall have 0, 0. We shall have 0, 0 there. And then the last one is when all of them take up zeros. So we have 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 rows. And then, of course, you consider now each case here. You see, like A or B, you see you have now A or B here. You can have that A or B like this, 1 on 1, 1 or 1, 1 or 1, 1 or 0. All these are ones. 0 or 0 is 0. 0 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0, you see. You continue that way, and then to the point where you get the whole of this expression, and therefore you make a conclusion whether it is a tautology or a contradiction. I think we are okay there. So now let's go to this. I was just giving you a hint to this exercise. I think that is C. So you're supposed to look at what you're supposed to do there. So I will leave that as an exercise. I've just given you the hint, similar to what we did last time under mathematical logic. No difference as such, but the difference in this case is that, of course, A, B, C take up 1 and 0 only. The same case also in mathematical logic. It only has 2 options, either true or false. And of course, in this case, true is 1, false is 0. Okay. Now look at this. Now we have a proving of Boolean equations. So we've crossed over from Boolean expressions. Whatever that we're dealing with here are Boolean expressions. Here we're dealing with Boolean equations, and you can see, of course, this one is equal to that. This one is equal to that. You are supposed to show that how this one is equal to that, how this one is equal to z. The whole of this is equal to 1. You can imagine the whole of this is equal to 1. How do we get there? The whole of this is equal to A plus C. So it looks like even B has been swallowed somewhere. If it is been swallowed, then there is something that it must be giving you an idea that there must be some absorption laws somewhere that were applied, and that is why something was absorbed. You can see B has been absorbed there. So you see, those are the kind of things that should come out in your mind. Let's look at the first one. In this first one, this one is A or complement of B. Of course, here we've juxtaposed and. You see, we've not indicated dot here, but you see there is and. There should be and here. But at times we don't indicate those ones. You can see, so I felt that I should take you through this and let you know that at times we don't indicate that dot here. So even if it is not there, know very well that that is silent there. So let me hope that you consider that. Now, here, We can factor out, you can see, when you look at this, you see that we have A and E appearing, A and A appearing. You deal with the left-hand side, get to the point where you cross over to this, using the Boolean properties. So here, we see that the first case that is preferable is to bring in A and A. You see, this one is A, or A and B. So you bring those ones together, and that is exactly what we have here. Then you factor out A. When you factor out A, then you have 1 plus B. But now, what do you know about 1 plus B? Of course, this one is 1 or B. 1 or B is 1. I think you know that, right? That is by identity law. You can see that. Look at this. Let's see. Let's even go back. Let's see the identity laws. Identity law. Let's see that. Oh, yes, yes. Oh, there is. Did I did not. No. Domination, sorry. That is it? Yeah, that should be domination, not identity. That should be domination, because then one is the one that is dominating there. Yes. Yeah. This one should be by domination law of that is of or. And you can see this. That one is domination. That is the domination. Check on that. Look at this. Yeah. You can see it is B or 1, and it is giving us 1, that is domination. And you see the reason why we call it domination is because that one dominates. And in as far as and is concerned, then we see that what dominates in that case is 0. Yes. So by domination law, so you can change this place. Yeah. In this one by domination law for or. And therefore you see this one becomes 1. You can see. So now look at this. Oh, yes. Look at this. We have now A by, you see, A and 1, because now the whole of this becomes 1. Then A and 1, in that case, A and 1 is A. And that is why we have A here. Now, when you look at this here, you see A or the complement of B, right? And C, this, you notice that, let's see what we call absorption law. Look at this. This gives us A or C, because A or C absorbs this. Yes, by absorption law. Look at absorption law again. Look at absorption law. Look at that carefully. Absorption laws. You can see. So you can see the whole of this is absorbed. You see. And when we have the whole of this absorbed, what happens in that case? Then you will notice that this one we shall have A. So that is by absorption laws. And what will happen in that case is that we shall get that to be A or C. Now, look at B. In B, we have this part and we have this part. Maybe let me enlarge a bit, probably to the benefit of those who are not seeing clearly. So the whole of this, we have some bracket here. You see, there is need for the distributive law coming in force here. So how about dealing with this first? When we look at this, you realize that this one is x plus, you see, that is x and y, of course. Plus, of course, we have that as or this one is and. So what we're supposed to do is to see how best we can manipulate that. Apparently, I do not know whether you can see that. Of course, probably you are not likely to see that because that is, you see, we're still learning. Look at that. What do we have that to give us? You see, this in itself, let me see whether, did I factor out everything? Yeah, maybe there was that. Yeah, it is here, yes. The whole of this gets absorbed. You see, this one, x plus the complement of x and y, or x or complement of x and y, will give us x plus y by absorption law. Yes. So this one is absorbed. So what happens in that case is that we shall have x plus y, and that is exactly what we have here. But now, these two, right? Check on that. These two, maybe I should ask you why, or you see, if this is one, then the negation of y is 0, 1 or 0, or 0 or 1 is 1. So we shall have here x, look at that. We shall have x or 1, and that is exactly what we have here. X or 1 is equal to 1, right? Because of that domination, you see? So we have that to be 1. Now we simplify this part by breaking, of course, it is by distributivity property. You can see this one by this plus this one by this, and that is exactly what we have here. And in having this, we have x and its complement. That one, it takes up the value 0. That is why we have 0y. And 0 and y, this one will still be 0. Now, this one, because of commutativity, we can interchange, you see, this y complement and y. And that is why we shall have, look at this here, we shall have y and y complement. You can see that, so that gives us 0 by x complement. And in that case, 0 dominates in that case, and that is why we have this to be 0. And therefore, we have 0 or 0, which is equal to 0. And now we have this part to be 1 or 0. 1 or 0 is 1. And that is how we concluding that this is the case as required. And that is how this reduces to 1. C and D are exercises, and you're supposed to work on that. Of course, following exactly what we've done here. What you're supposed to do in these two cases also make reference to what we've done here, together with the Boolean, the properties of Boolean algebra. These ones here. And you should be able to show the other side comfortably. And please be doing exercises. That is my plea. Be doing exercises. If you are left with exercises, kindly please attempt, because those ones expose you further. So those two are exercises, and that marks the end of Boolean algebra. We have 12 minutes left. Maybe what I would wish to do in this 12 minutes is to just introduce you to graph theory, so that when you're reading, at least you have an idea what we call graphs. And this is the last topic, graphs. Let me confirm whether fellows can still hear me. Kindly please raise your hand just in case you are getting me clearly. Ah, perfect. That is okay. Yeah, I like how fast you guys are. You are very fast in responding, and I like that. It's something that I don't take for granted. Other fellows at times take too long in responding and so on. I like the way you are very swift. I think indeed I've enjoyed having a lecture with you guys. It has been good, and yeah, I'm impressed by the way you are so proactive, and that one I like. What I would wish to raise, just in case we meet ahead in any other unit, is for fellows to at least ensure that at least, yeah, watu wajichoche kiasi, ndio sasa watu wawe wengi in attendance of lectures and so on. Yeah, so that is it. So look at this. Let me give you an idea of what graphs are. You see, when we talk about graphs here, it is not the usual graphs that we deal with. You see, like bar graphs. You see, probably that is what some of you are thinking. Bar graphs, we have what you call histograms and so on. No, That is not what we talk about. We talk about graphs here in a different context. And the context in which we present graphs here is that we present graphs in the form of vertices and edges. You see, you have points and edges. And when we talk about edges, we're talking about simply those lines that connect two that is two vertices. They could either connect to two, or at times even could be one. You see, there is a likelihood that maybe the terminal point, or rather the initial point of a certain curve or of a certain edge, is not connected to a vertex. Yes, somebody, I do not know whether is there any issue. Maybe I can let me see. Okay, a paragraph. What do you mean by paragraph? Can we come out? Yeah. Or probably you're thinking about something. Yeah, you've just mentioned paragraph at the moment. You're talking about a graph as a paragraph. Come on. No. So look at this. When we talk about graphs, we look at this. This is a graph. You see, these ones are called vertices or nodes. Look at this. Maybe let me do this. Okay. You see, these ones. This one is a vertex. So, like, how many vertices does this graph have? It has 7 vertices. 1, 2, 3, 4, 5, 6, 7. And these ones are the edges. You see, these are edges, and they connect. Now, how do we present it? Look at this. G is presented in this form, where V represents the vertices. E represents the edges, right? That is it. You can see that. So you can see this V. It is a non-empty set. It has to be, there must be some vertices, otherwise that is not a graph. You see, that is why they say that non-empty, it can never be empty. We either call them vertices or nodes. And then E now is the set of edges. And each edge is either one or, you see, 1 or 2 vertices, or rather has either 1 or 2 vertices. That is what I mentioned. There could be a case where maybe there is no vertex here. So there is no dot here. What we have is just but these 2 vertices meeting, but apparently there is no node or there is no vertex. And in that case, therefore, you notice that some of the edges, then in that case, will have only 1 vertex. But many times, of course, you're going to find edges that have 2 or more. No, two vertices, sorry. And you see this edge, this like the endpoints of this vertex, of this edge is V1 and V2. The endpoint of this edge is V2 and V3. The endpoints of this edge is V3 and V4, and so on. Now, look at this. We use curly brackets here. This one represents what we call undirected edges. Undirected, there is no direction. You see, when we have directed, we have an arrow. You see, we have an arrow. Those ones are directed. Now, when they're directed, we use curvilinear brackets. These ones, that is the difference. Please, we use curved brackets, right? So you should be able to see that these ones are undirected. And you notice in this case, you can see this. I think this is important. These vertices, we could either use small letters or capital letters. Any can do. Look at that. So don't get surprised in situations where you come across vertices that are presented by maybe capital letters or small letters. Any can do, right? Yeah. And we're told here a graph in which each edge connects 2 different vertices. Look at that. Each edge, like here, you see each of these edges are connecting just 2, right? 2 different vertices. And there are no 2 edges that connect the same pair of vertices. You see, you can see here, and you're gonna see just down there what we mean by that, right? Look at this. You see, the other one, the one that is not simple is like this one. Look at this. If I have another edge connecting these 2 vertices, you can see we have this edge and that one. This one now is not a simple graph. But this one, as it stands right now, is a simple graph. You see, this one is a simple graph because there is no there are not two particular vertices that are connected by more than one edge, right? That is what we call a simple graph. A multigraph, so that you can see that now, that is when now we cross from a simple edge to a multigraph. That is when we have multiple edges. You can see now this is what we mean. You can see we have two edges here in as far as V vertices V2 and V3 are concerned. Like even here we have three edges in as far as V3 and V4 are concerned. This one, that, and that one. You see, and then you see we have two edges here. So this one is a multigraph. You see, and you notice that we have the simple graph, but now plus multiple edges between 2 points to allow multiple edges. You can see those ones here. That is a multigraph. When we have what we call a pseudograph, pseudograph is when we have a loop. You can see this one. You could have a loop maybe that is moving that way from that point to the same. That is what we mean by a loop. You see, this one is a loop. So when we have simple graph, you can see, yes, we have a simple graph here, multi-edge because of these ones. And then now we have a loop also. When we bring in a loop, then we shall have what we call a pseudograph. So we're progressing bit by bit. Now, in the case of directed, which I've mentioned, this one now you can see we have an arrow. You see, look, you can see this one now we have a loop. And then you see now we have two edges here, you see. And here, well, these ones are called multi-edges. And you see from U to V, from U to V, these ones are not multi-edges. You can see these one are not multi-edges. You can see this one is from U to V, and this other one is from V to U. Now these ones are not multi-edges. You must get the difference there. Now when we talk about directed multigraph, of course we have a digraph. You see, a directed graph is called a digraph. And in this case, we see that if we have a digraph plus multi-edges, then we have what we call a directed multigraph. And what summarizes all this is this table. And I have asked you to note that the difference in the types of brackets used, you note that difference in the types of brackets used, denoting undirected edge, which is this, what I've mentioned earlier. And this one represents directed. You can see, that is why you can see this one. You can see the type of graphs that I've used here, directed. You can see, compared to these ones, compared to the first ones, and you can see these ones we used curly brackets. So get the difference and ensure that you register that in your system. Now, these are the terminologies that are very important. If anything now, when you read their head, you will find that things will fall in place without a struggle. These graph models that I'm talking about here simply give us an idea of areas where we can apply graphs. You can apply it to represent interaction of different species of animals. You can see we can apply it in acquaintanceship, what we call acquaintanceship graphs, where we have, you see, people are acquainted to each other. You see where so and so is known to so and so and so on. And you see these ones are equally important. And again, of course, one area that not even in the case of influence graph, when they're studying what we call group behavior, but now the part that you see that is likely to be more important in your case are computer programs that are normally executed more rapidly by executing certain statements concurrently. And that being the case, I would ask you to be very careful in looking at this, see whether this one, look at this carefully, see how you can make sense of that in as far as that example that is especially crucial in your area, what we call precedence graphs and concurrent processing. Yeah, how is it instrumental? So kindly look at that. Of course, there are some exercises here that engage you through. Please be doing exercises, and that is something that I've told you. So look at those exercises. They are straightforward exercises. In the event that maybe there is a challenge and so on, we can have we could have another meeting and see how best we can handle that. Now we have graph terminology, and these terminologies are very crucial. What I'd suggest, because it's already 6, maybe I'll need some your patience briefly but we are almost closing. We are almost concluding. Under graph terminology, these terminologies are very important. Like in this case of adjacency, you realize that when you're talking about adjacent and the degree of a vertex, these ones will come in handy later, especially. Well, look at this. When we are when we are dealing with what we call adjacency matrix, you see, a cycle will be important. You are supposed to look at that, sure that you understand what a cycle is. Also, when you talk about a subgraph, you see a subgraph, like in this case, obtaining a subgraph from this, you see, you notice that, look at this here, this is a subgraph. All that it does not have, it doesn't have D, the vertex D, but you realize that this one is extracted from this. You can see it is this one. That is a subgraph of this graph. And then look at this. I was taking you to adjacency matrices. You can see this. Adjacency and terminal vertices first, even before we talk about adjacency matrix. So which vertex is, you see, which vertex is adjacent to another one? You can see that. You can see A is adjacent. Adjacency vertices are B, C, E. How do we have that? You see, we have A. What do you mean by adjacent vertices? You see, there are vertices where there are edges. You can see this one connected to A, B, C, E. You can see those are the only vertices that are connected to A through these edges. You see, those are the ones. Like now B, how is it adjacent? It is adjacent to A because you see it is connected to A, and that is the only one. Look at this C. You see, when we have C, you see the adjacent vertices in that case are A, E, D, and that is exactly what we have here. Now, for those ones that are adjacent, this one, remember, this one is in as far as undirected. You see, this one is undirected. Undirected graph. Now, where you have adjacency, you see, you could come up with what you call a adjacency matrix. How do you come up with adjacency matrix? You realize that you have A, E, C, D, E, and then you have here A, B, you come down, A, B, C, D, you see C, D, E, and then now where we have an edge, like A is adjacent to B, like here is A is not adjacent to that A, so that is 0, but A is adjacent to B, so you have 1. A is adjacent to C, you have 1, you allocate 1 where we have adjacency. A is adjacent to E, but A is not adjacent to D, so there is 0. You can see that. B is adjacent to A, yes, of course, this one is an undirected graph, you see, but now it is not, you can see that it's not adjacent to these others. So you can see that we shall have 0, 0, 0, 0, and so on. So you notice that now you must have an understanding of those terminologies before crossing over to this point, you know. And basically, they are straightforward, but I would not want to assume that everything is straightforward. No, that is not the case. So that is why I would want to see how you guys will get this as you go through. So you have what you call adjacency and terminal vertices. And then now in a diagram, you see now there is something different there. You can see when you're talking about the diagram, initial vertex, we have what you call terminal vertex, because you see we have a starting vertex where the arrow is heading to, that is the terminal one. So now you realize that when it comes to adjacency with respect to diagrams, it's slightly different. So kindly know that and ensure that, yes, you have those ones, so that when you come to adjacency matrices, you can see what we're talking about here. You see that we are locating one where we have an edge. Where there is no edge, we are locating 0. You can see that, yes. That is something that you should see. And in the case of a pseudograph, of course, you see we have even the case of loops. So you can see we have multi-graphs, multi-edges, you see. So when you have multi-edges, in such a situation, then, like in this case, you can see you are counting this. You see the A and B, we have how many? 3. And that is why you can see we have 3 there. You can see that, yes. So in a pseudograph, you realize that it does not have to be only 0 and 1. This applies to a simple, maybe could apply to a simple graph. You see adjacency matrices. So that is something that you should have in mind. And then, of course, again, you must you need a clear understanding of what we mean by incidence matrices, because these are things that will come in handy even later beyond examination, because we don't only prepare for exams. So you see, and you can see where we are. We are almost at the end. And of course, once you are done with that, there is what we call connectivity. Connectivity is also some part that is very important. And before connectivity, of course, you are supposed to know what a path is. You are supposed to get the difference between a path, a trail, and a walk. You see, look at these points and edges are unrepeatable. Of course, when we're talking about a trail, it allows duplicate points, path not repeatable. When it comes to a walk, allows duplicate point and duplicate path. So you must get a difference. And of course, you see, we have those examples to give you what a path is. Look at this UV, UVY, that is a path. But now when you see a trail, look at this. What is repeated? You can see V is repeated, you see? And then when we have a walk, what happens in that case, it allows duplicate points and duplicate paths. So that is something that you should be able to get a difference from, and especially based on what has been displayed there, I want to believe that you should be able to piece that comfortably. And once you have that, then you go ahead now to talk about a cycle, a circuit, and a closed walk, you see? And here again, we have some examples. And then now once you have that, then you cross over now to connectedness. When do we say that graphs are connected? When do we say that it is disconnected? Kindly please, I think your patience has been good up to there. Go through those ones. I'm likely to throw in some questions relating this last topic to see how much you've had a grasp of this. Okay.